Nope. Do you have your ammo loaded?
No, I just thought I'd see what things you provided me with during your talk.
Yeah, actually, we might as well use the other projector too, right? And you could at least see what's going on.
Sure.
Back to it up. Okay. What? I'm gonna be. What?
Getting the chairs out of my way.
Okay. Oh, you didn't have a clicker?
There's one.
There may not be time to set it up.
The one that I found.
Give me a second.
Okay. Oh, wait a little bit longer.
Okay.
I guess.
Rush.
Yeah.
I don't know if this has a USB or
What does he need?
the clicker. I don't know if it has a.
Oh, a clicker. That'd be nice. I need more chairs. Nope. Wait. Onto the chair right there. Oh, I guess.
Still doing chairs?
We're getting pretty close.
Here you go. Get there.
One of those is the pawn cards.
Oh, right. One there, though. All right.
Oh yeah, there's another one here. Oh, there's another one there.
There's two.
That's other theses.
I think this is the only one. All right.
You always eat it.
So left to right, and that's the
one.
All right. Try it. Okay, great. Okay. You all set?
Yeah, I'm all set.
Okay. Welcome everybody to I think the only physics thesis presentation here. But that's okay. I've heard a lot of great theses over the last couple of days, and I'm looking forward to hearing another one. It's gonna be good, right?
Sure.
Okay. Almost all of you, I hope, know Ryan Farber. He hails from Southern California, sunny, not Southern California. Well, it's not all that sunny either. Anyway, he always talks about how he's gonna, go back there, because he loves the place. So for grad school, you're going to
Michigan.
It's almost California.
Close enough.
Yeah, halfway there.
Give or take 2 feet of snow. Anyway, so Ryan's going to be talking about his work trying to do computer simulations of magnetically active fluids using the Python programming language. So take it away, Ryan.
Wow, you just broke down my title, taking up about half my talk. So I can just make this 10 minutes and go home, right? No, I'm going to probably reiterate that. So you heard my name, you heard what I'm going to talk about. Let's get to it. I'm going to start out by giving you an outline, seeing what I'm going to talk about. First, we're going to go into definitions of what's a fluid, what's magnetohydrodynamics, why do we care, the motivation. Because the motivation in physics is really important. We care about the real world, and there's some really cool stuff that we described. And then I'm going to go into the physics. The Argo is the name of my code. It's named in honor of Jason of the Argo, who is my advisor and has had to put up with me. So moving on. What is a fluid? The answer is more than you think. You might think of fluid as being liquids like water, but there's really a whole lot more to it than that. If you're from chemistry, you might think of aqueous solutions. Gases also count, and even stuff like glaciers, if you've got the right time scale. Whoops. I guess someone might need to hit play for that one. So this is from a
Using
Nova
a fixed
program.
camera mounted 650 feet from the ice, Luke has created a one-of-a-kind
This is
movie of a
Mount
glacier
Blanc.
as it moves over the course of a year.
And so you hear the spooky music. It's weird because like glaciers are solids, we think. They're not supposed to move, but they do. What's a fluid depends upon the time scale. And the sort of definition of a fluid is that no matter how small of a shear force you apply to it or shear stress you apply to it, it's gonna flow. It can put up resistance, but not enough to stop it. That's the only difference between a fluid and a solid. So moving on to some motivation. This is the more mundane example. I'm the weatherman. Here's high pressure, here's low pressure. And you can talk about it's rainy here, thunderstorms there, la dee dee da. So that, I mean, that's really important, but we're going to be talking about some cooler stuff, in my opinion. So, for example, a lot of people fly. That wasn't possible 120 years ago or so. Otto Lilienthal, German, back in the 1890s, was the first human aviator. He built some gliders. He actually flew a little bit. Then he died because of one of his gliders. He crashed and fell. But that was a direct inspiration towards Wilbur and Orville Wright, who came up with the first airplane about 20 years later, or within 20 years. We've improved since then, and we've got some really cool airplanes now. So this is a Boeing 737, and Boeing is producing bigger and better planes. The military is also interested in planes. This is a NASA built model of maybe a futuristic plane in a wind tunnel. This is my friend's model, Thomas Matthews at University of Washington, and airplanes are just getting better and better. They're really important in terms of the military and in terms of getting from places A to B, which a lot of us do. I do a lot. So that's kind of fluid dynamics. Fluid dynamics is how fluids change over time, and the study of that. Magnetohydrodynamics, first thing you might notice is, why hydro? I thought you said like there's a lot more to fluids than water. That's just some dumb, old, arcane terminology that I'm stuck with, unfortunately. It really is magnetism of fluids, no matter what that fluid is. And you do that with just classical Maxwell's equations of electromagnetism with the fluid equations. So why bother with this? Like, when do we see this in real life? We can use fluid dynamics to describe airplanes and the weather and whole tons of stuff. Where does this show up? It does matter, and it's really cool in the ways that it shows up in astrophysics and a more terrestrial example that I get to. The first example is solar flares. These are big events on the sun that are actually kind of our best example of magnetic field lines in astrophysical situations. It's caused by magnetic field lines reconnecting, which I don't have time to go into. It's a really cool subject, but magnetic field lines can get really twisted and change in the direction so that they can line up and cancel and blow up, essentially. Blow a explosive piece of the sun out, and this forms a big part of space weather. So there are solar storms, and that shoots a whole ton of particles towards the Earth, and that's like bad news for Earth. There's spacecraft and satellites that can get disrupted by those solar storms. You want to be able to predict that. So we've moved on to boring regular weather, and we're talking about space weather. So that's cool stuff. There's also some pretty beautiful parts of it. The aurora that we see near the northern and southern poles. Those are caused by those solar storms. The particles getting funneled along Earth's magnetic field lines and getting drawn towards the North Pole and South Pole, interacting with the atmosphere and creating these beautiful lights. So that's another thing we learned. This is a really cool simulation. It's actually of a hydrodynamic simulation, so it doesn't include magnetic fields, but it's by this guy, Jim Stone, who wrote a code that I'll be discussing later. And this is still pretty representative of magnetohydrodynamic flows around black holes. The accretion flow, so that's particles moving in the a disk that the black hole is going to sort of swallow up later on. And again, that's just touching on it lightly as an application. So the more terrestrial example, the Florida current. In between Florida and the Bahamas, there's this current that we've measured with cables going below at the floor of the water. And it turns out that there are magnetic fields oriented in a really nice way there. Magnetic fields produce accelerations of charged particles, positive in one direction, negatives in another direction. Because water is slightly polar, and the magnetic field, I guess, is strong enough, you can set up a potential difference, which is measured by this ammeter, of the current in between the 2 points. So that's another example. So we're gonna skip the examples now and talk about what my simulations are doing. And to do so, we look at a sort of Hollywood way of life. We break up time and space into chunks. So space, you're kind of used to being chunks in terms of pixels on computer monitors and so on. Time as chunks, you're kind of used to from movies. Maybe not all of us are old enough to deal with film reels the whole time, but that's kind of how even digital movies work. They're just a whole bunch of frames of pictures. All right, so moving on. These are the magnetohydrodynamics fluid equations. There's a lot of them. The first one describes how the velocity changes with time. And there's a lot of terms there. We're going to break this down, so don't worry about it too much. The second one is a tracer concentration. So think of that as like dye being put in water and seeing how that dye gets moved around by different effects. This is the vector potential, which is defined so that its curl is equal to the magnetic field. And two equations which should have been on this slide, but I guess didn't make the cut for some reason, are the divergence of the velocity is 0, and that means that velocity can't pile up in any one place. You don't have, we're not considering any changes in density. That's why that Gulf current example was really relevant, because water is a really good case of an incompressible fluid. The other equation that's missing is divergence of the magnetic field is also 0. And that's one of Maxwell's equations, and it has a similar interpretation. All right, so we're gonna move on and talk about advection. So advection, it looks like this is not the most recent version of the PowerPoint, but that's okay, is this term here. It's u dot grad u. So what that is saying is that velocity carries itself. You started out with a hat function, something that just looked like a hat, and it's getting carried to the right by the velocity field. The velocity field is moving to the right. The hat's actually velocity itself, so the velocity is carrying itself. And that's a strange concept, I know, but that's what that term means. Oh, there it is. So diffusion is another term in the equation of motion for a fluid, how the velocity changes with time. And that just describes, so diffusion is when any sort of system is spreading out over time. And you can see that from that simulation there, which I can play again. Maybe. There it is. So in our case, we use the new subscript because it's viscous diffusion. So viscosity you're kind of used to. It some things are harder to flow than others, and that's describing how velocity kind of shears against itself. There's resistance So if you rub your hand around, there's friction. For fluids, there's also friction between fluid layers, sort of. And that's describing that. Next thing is we want to make sure that divergence of velocity is 0. We actually use our pressure term to do that. And this is a simulation. All these simulations were with my code, by the way. This is another one where it's showing velocity started out 0, but it's set equal to 1 on here. So you can think of a conveyor belt moving fluid. Now, if you have fluid just moving over here, it's going to pile up at that corner. The color represents pressure contour. So you have high pressure here and low pressure in that corner. So the high pressure exerts a force proportional to the gradient, which pushes that fluid down and sets up this cyclic flow. So that's what's going on with grad P, and we use it to remove divergence from the velocity field. So we have the Navier-Stokes equations right now. Next thing we want to do is talk about that tracer concentration. So lots going on in this simulation. The colors represent the tracer concentration, and over time it got weaker and weaker. That's because the tracer is diffusing out, and you're only seeing the strongest bits in red. Hopefully I can play that again. So the arrows are the velocity, and they start out in 2 vortices, and you kind of lose them, but you can still see where they are from the tracer concentration. And so they get moved around along the wall, and I won't have time to get into that, but if you read my thesis paper, I describe why that is. So what you have is the tracer concentration gets moved by the velocity field, so we have another advection term, and the tracer concentration diffuses out also. So we've presented the Navier-Stokes equations for fluid velocity and how a tracer concentration gets moved around when it's not affecting the flow at all. The next thing we want to talk about is how that got implemented in the code. So that would be maybe more interesting for some of the CS people here, like I see Angel and Nathan and Jesse and some people from CS here. So to do this, we approximate derivatives as, well, what we really want to have derivatives. We think of derivatives as slope. That's what these graphics are kind of showing. And finite differencing is when we take a point and look at neighboring points. And so we break up the problem in that way. We either take a step back, so that's the backwards approximation, or we take a step forward, that's the forward approximation. Or we look sort of backwards and forwards and average to find the value in the middle, and that's the central approximation. And almost all of the derivatives, or all of the derivatives initially were discretized or made into sort of computer comprehensible way with finite differencing, and then we improved something. So yeah, this is not the final PowerPoint, but oh well. So this is kind of the graphic that I want you to focus on. And you have fluid that you want to end up at the center because we define our variables at cell centers, where each little box is called a cell. If we backtrack, we find that that fluid is not at a center. So we don't have its exact value. We have to linearly interpolate its value from neighboring cells. So that's what the backtracking method does. And it's nice because it's much more stable than the finite difference method. And if you want more information on that, you can ask me at the end or read my thesis. This is a different way to discretize the advection. So relaxation method is how we actually find the pressure that was mentioned to remove the divergence of velocity a little while ago. So this is a Poisson problem because we've got div grad of a variable equal to some non-zero term. U is called the source term, and it's defined and set up and calculated so that it's equal to the divergence, so that when we calculate grad P, we're removing divergence from the problem. So we've talked about a number of things now. We still need to talk about the magnetic terms. These two in the equation for the velocity field, this whole equation of motion, and how we get magnetic field from that. So this is where I really need the actual PowerPoint, I think. But no, it's okay. Grad B squared over 2, that's the magnetic pressure. The reason why there's a magnetic pressure term is because of Lenz's law, which some of you from intro physics, like Angie and Kim and others, should know. So if you've got a whole lot of, if you've got an increase in magnetic flux through a surface, like the magnetic field lines, which I won't have time for the proof of, but they follow the fluid velocity. So if you have fluid constricting, then the magnetic field lines also constrict. So that if you're going through a constricted pipe, there's going to be more flux through that surface, and that magnetic field doesn't like that. Lenz's law says that you try to keep magnetic flux constant. You don't like changes. So there's that magnetic pressure term trying to counteract that. Magnetic self-advection is actually also called magnetic curvature term, and that describes how. So if you have a tokamak, which is one of the main ways that people are trying to do fusion experiments now, it's really just a torus, and you have particles going around, and you have magnetic field lines following the particles. There are some field lines that are more curved than others. The ones that are closer to the center. The ones further out are less curved. And this describes how that induces forces on the particles. And you get this term from, you derive it from Maxwell's equations and the J cross B Lorentz force. And writing it in an alternate way, you get this phrasing, which is nice because it looks like an advection term. But it's a little bit more complicated than that. All right, so this is kind of the frontispiece of the presentation. This is the Orszag-Tang vortex simulation. It's a 2D, fully ideal magnetohydrodynamic simulation. So we started out with magnetic fields. I guess you couldn't see it because it goes too fast, but some magnetic fields, there are going to be 4 sort of magnetic field loops. There you go. 4 magnetic field loops along X, 2, and Y. And what that does, because, well, I guess it's helpful to look at the how the velocity field changes also. So there's 2 vortices for the velocity field, and because there's that the extra 2 in the magnetic energy, you get it so that there's a sort of preferential direction of motion of the system. It doesn't just stay simple. So this is comparing my code both times on the left to Athena, which is a sort of tested and true MHD code, which uses much higher order solvers, so it's more accurate, and it includes more physics. I wanted to try to make it incompressible, but it seems like it's sort of fundamentally compressible, which means that they take into account changes in density that are much more relevant for gases and astrophysical effects. So there are some very noticeable differences between these two. If you look at the magnetic field simulations in particular, though, there are some noticeable similarities. And so Jason and I sort of think that The code does a pretty good job of handling magnetic time evolution, and it's a little bit more questionable how well it does for evolving the velocity through time. And so I want to close by saying that saying that part of the reason for this is not just, oh, I can do this, look at what I did. It's, I did this. Some of you can do this too. Moses, I think, is a freshman. Maybe you're more interested in math, but this is something that I did to try to help people enter into this field, because Athena, which I've been showing the simulations for, is written in C, or you have the alternative of Fortran. Those are kind of ancient languages and aren't that nice to read, and in my opinion is not documented that well. The Argo is fully written in Python, and then I've done my best to write it as legibly as possible. So if you want, I can show you the actual code for that later. Are there any questions?
Jason, what's the format of a physics defense?
I should mention that. So there will now be a period of open question and answer for the whole community. Ask any questions you like. We'll probably do that for, well, as long as we have questions. And then we'd like to invite everybody but the committee to leave while we grill Ryan privately. And you know, hopefully try to stump him, because that's our job. Anyway, so that's basically it. So if anybody has any questions for Ryan?
Yeah, Henry.
What is the strength of these magnetic fields?
What's the strength of them? So one thing that I didn't get into is the law of dynamical similarity, which says that for fluid problems, and this is also true for magnetohydrodynamics problems, you can work in totally non-dimensionalized units, so that you can scale up your problem. So those, like my friend's airplane model that I showed you, is very small compared to like a real airplane. But because of the law of dynamical similarity, you can test flow along that surface and then scale it up. So that sort of magnetic field strength question that you're asking is kind of irrelevant. I mean, in terms of the actual value, I think that it started with the value of 0.4 and dropped down to 0.3 or so. I mean, we can take a look. It was probably hard to see the color bar from here, but the color bar shows how that changed with time. Oh, that one's covered up. Do you want to switch? No, I mean, it's too late now. Yeah.
I was only wondering because I'm not a physics person. I remember the right-hand rule. Magnetic currents will produce electrical fields, and I was wondering if there's any studies about conductors in fluids producing electrical current.
So I mean, if I'm understanding you right, that's kind of why that Florida current exists. So the there's a magnetic field going out of the Earth, as I understand it. There's currents going perpendicular to that. Water is just flowing along the surface of the Earth. That causes a magnetic force from the right-hand rule. So let's see, V cross B. So you should have flow to in this direction and this direction. So you had positive charges on one side and negative charges building up on the other side. And that's why you could detect that that current in the Florida current. Any other
If I
questions?
could jump in, then one way to answer both of your questions at once is to say that his simulations are designed so that the right-hand rule forces you're talking about are equal in importance to other physical forces within the fluid, like, for example, pressure and the advection flow term. So the answer to magnetic, probably because the magnetic force is big enough to matter of equal importance. That's what we need to find out.
Okay.
So you said that the simulation was kind of non-dimensionalized, but getting to, say, that Florida problem,
Oh, yeah.
I mean, is the code set up such that you can put in real material properties fairly easily and simulate something with that is, say, salt water flowing in a certain rate?
You'd have to set up a normalization, and I would have to do some literature reading to understand that better. That was a big problem of my work over the summer, is we were working with this code that someone else set up, which was, because almost all codes are in non-dimensionalized units, it just makes everything a lot easier. But we wanted to apply it to the Milky Way's magnetic fields. And so to make sure that we're actually simulating that and not something totally different, we had to read these papers to check out what the normalization procedure was. So there is a process, and it should be totally doable, but I don't know how to do it.
This is one reason why I hate non-dimensionalized models and like to put in actual number dimensions. But you didn't, so okay. Other question?
Okay.
So many burning questions that I better start now.
Okay.
I'll save them for later. So I think one thing that we learned from our intro physics classes are things like energy, angular momentum, and momentum are conserved. Right? So
Yeah.
how well does those things, how well does the conservation of energy and momentum work in your course?
Yeah, that's a good question. And I mean, you can sort of solve almost any introphysics problem either by considering conservation of energy, broadly defined to include momentum and so forth, or thinking in terms of forces. So I've kind of set up my problem in terms of thinking about forces, but there is still a question of, am I conserving energy? I have a set of Python scripts that calculate how the maximum velocity changes over time. So that would get you how kinetic energy is conserved or not conserved. And in certain simulations where you're not ensuring that the velocity or magnetic field are divergent free, and in cases of numerical instabilities, velocity can grow up, it can exponentially increase in a way where you're not conserving energy. But the simulations that I showed you are either inviscid, where the velocity stays about the same or goes less because of numerical diffusion, or they include diffusion so that kinetic energy is dropping away. So you only have kinetic energy conserved when you're not talking about friction, right? Because there's the energy of the whole system, energy of the objects in motion, and then energy lost due to friction.
But the total energy within the system should stay constant.
Right, if you can measure how much friction there is. And I don't think that the code can allow that. So, for example, near the beginning, I was showing the hats advecting, and they were getting damped really quickly, even though I was just talking about advection. That's because there's numerical diffusion. So I talked about that diffusion term. Even when you're not including that explicitly in the code, there's just from how you discretize things, there's always numerical diffusion, that sapping energy away.
Sapping energy and converting into?
I would think of it as heat energy.
And that has?
Heat energy has energy. I mean, what are you asking?
Pressure.
Oh, okay.
Thermal energy is not accounted for in this model.
No. Any other questions? Do you want to check if there's any online questions?
Oh, right.
I said we'd check. Nope, no one commented, so we're all good.
Right.
Yeah.
So just wondering, as somebody who's had experience in these programs, could you explain how your model and the OnSig model differ in terms of like explanatory power or other things?
Could you say that last half again? How
Oh,
do
yeah.
they differ in terms of?
In like their explanatory power or other things that I don't know
So Athena is a full MHD code. So it can deal with, I mentioned how we assume that divergence of velocity is 0, so that fluid can't pile up in a place. Real fluids, you can't have fluid pile up in a place. You can squish water down. It's really hard to do with water. It's a lot easier to do with gas, for example. You can reduce the volume of a container of gas, and that increases, that squeezes the gas closer together. So Athena covers that. It also is much more accurate. So I was talking about using finite differencing, which has a truncation error proportional to your delta x, your cell size. This is a third order model where it's proportional to delta x cubed. So that, and delta x is less than 1. So it has a much smaller error compared to my model. Also, my model, as Jason said, is isothermal. It doesn't depend on temperature. It doesn't include temperature effects. Athena can do adiabatic and other, it can include temperature effects. So it can do a lot more, but it's pretty freaking hard to read. So it can do a lot only if you understand it, and it's hard to figure out. It's hard to understand it. Gotcha.
So if you did want to do compressible flows, for instance, in order to do gases or plasma or something like that, like what would you have to add to your model?
So the equation for that is
you take one term out from one of your, or you take one of the equations out, right?
Not really. So the divergence of velocity equal to 0 constraint is simplifying del rho, that's not a vector, del rho del t plus divergence of density times velocity equal to 0. So when your density is constant, you're not having a change of density over time. And you can also pull the density out of that divergence equation. So you need to model how density changes with time, essentially. And you have to figure out how you discretize this, this term.
Now, is that especially hard with your scheme of tracing backward from where a particle came from then?
It would, well, so that's for advection.
Oh, okay.
So that's kind of a different,
okay,
no, so that's a good question then. The backtracking scheme only applies to advection.
Okay.
And it's not applied to all the derivatives.
The big challenge with incorporating that term is it begins to permit the existence of sound waves in the fluid. Right. And then you've got two different processes which can move energy around, both the physical motion of the fluid plus sound waves bouncing around, carrying stuff around. That often has big numerical consequences in the difficulty, in the time it takes to get a solution to the code. So that's why I encouraged him not to try to do that. Right. More questions? That's it? All right. Well, thank you guys very much for coming.
Thank you all for coming to listen. And I think you're all about to be asked to leave. If any of you want to hang out, I'll hang out with you. I mean, we might do something. I don't know what I'm saying, but
You'll deem to be seen with you.
If you want to hang out, we might do something. Yeah, I guess be out of sight or hearing, but we might do something after they release me. Okay, the end.
Good. Not six. Like some students are already taking it starting.
Oh, thank you.
You're welcome.
All
All right,
right,
great.
great.
I'll stop by around 2 and I will
Ryan,
be
I'd
by
like to
your
request
office.
though that the streaming end now.
Oh, yeah, you're right. Yes.
Yep.
It absolutely needs to.
I'll be right back.
Thank you.
A little bit premature.
Okay, well, presenting is an accomplishment.